This video is part 4, and it's the next to last video we're going to do on queues and arrays. And in this one, we're going to be implementing, stacks and queues. In this one, we're going to be implementing queues with arrays. So in the previous video, we did stacks with arrays, and that was fairly straightforward. It turns out when we try to do queues with arrays, there's some difficulties we're going to have to overcome. And the problem basically is that unlike a stack where you're always dealing with one end of the array, so you have the fixed beginning of the array as you add to the stack, making the index numbers bigger. When you delete from that same end, so you're okay. But the problem is with a queue, you're having to deal with both ends, both the front and the rear. Okay. So to get started and look at an example of the problem we're going to have, let's just say that we're going to have two new variables we're going to add. We're going to have a queue front, which points to the index of the first element in the queue. Okay. We're going to have a queue rear that points to the last. So we're going to start with an array that we've already, or sorry, that a queue we've already added some things to. So we've done an add queue 7 and then 2 and then 3. And I just jumped all over the place. Let me jump back to where I'm supposed to be. I love when your cursor is not where you think it is. Okay, here we go. So this is what we have here. So we have the 7 went in at the front, then the 2, and then the 3. Okay, life's good. The queue front is equal to 0. So that list sub 0 is equal to 7. Queue rear is equal to 2, and these red numbers are the indexes here. Uh, the queue rear is equal to 2, and that means that list sub 2 is equal to 3. Okay, and we didn't mention it, but there will be a queue max, which this case is equal to 10. We have 10 items that we can have. Okay. So we're going to add another one here. We're going to add an 8 to the queue. Okay. So to do that, we're going to increment the queue rear to 3 and then add 8 in that spot. And that's what we've done. Okay. Life's good. No trouble. So now we're going to have some trouble in that we're going to pop off the item. Okay. The mechanisms of the pop are straightforward. All we're going to have to do is increment the queue front from 0 to 1. Okay. The queue rear remains the same. The problem, though, is that now this memory location where list sub 0 is held is not accessible anymore. It's wasted. Okay. And if we keep popping off, it's going to continue to be more of a problem. Okay, so here's an example where we've popped off 3. Now things still work in that in this case here, 8's all we have left. The queue front is 3. That's the first element. That's correct. The queue rear is 3, and that's correct as well. But we have now 3 wasted spaces. Okay, which we don't want. We're going to run out of space more quickly. Okay. So to deal with this problem, we're going to use this concept of a circular queue. With a circular queue, basically, when we get to the end, okay, so when the queue rear is equal to 9, in my example, and you want to add 1 to it, we're going to go back to 0. And we're going to do this using the modulo operator, okay? So here's an example where we have the same, we've popped off 3, we've added more items to now where the queue rear is now at 9. Okay. So when we do an add now, the add queue 22, we want the queue rear to go to 0. Okay. Like this. And now it gets added there. Okay. So we're going to accomplish this using the modulo operator, which is the percent sign in most languages, certainly in C++. So the way the modulo works is it takes the first number divided by the second number, and the modulo is what remains. Okay. So in this example, to calculate the queue rear, instead of saying queue rear plus 1, we're going to say queue rear plus 1 mod max queue size. okay, which is 10 in our example. So note that if we're anywhere else in the list, if our max queue size is 3, we add 1 to it, it's 4. 4 mod 10 is 4. Anything less than 10 is going to be just what it is. Okay. So all of those numbers work. But when we get to 10, so now we're at 9. So we have 9 plus 1 is 10. 10 mod 10 is 0. When you divide 10 by 10, you get 1 with no remainder. Okay. So that's how that's going to work for us. Okay. And what has that just done? I think I'm using the mouse keys and the keyboard keys, and that's a problem. Okay, so that's what we're gonna do. Okay, and we'll see the code in a minute. A complication of this is that it's going to be difficult to figure out whether or not a queue is empty. Okay, if we didn't have this complication, we certainly could, based on if the two queues were if or sorry if the queue front queue rear were crossed, then we know that we must be empty. Okay, but that's not the case because of the wrapping around of the circular array. Okay, so easy enough to fix. We're just going to go and add a count variable. Okay, so we can keep track of the count. If the count's 0, then we know that we're done. Okay, that we're empty. If the count is not 0, we're not empty. So that's easy enough to do. Okay. The last thing we have to think about. Okay, and I don't know what I did there. That's probably what I meant. Okay. And I got to correct that as well. Okay, so it's when we initially set up our queue or we initialize a queue, either one, okay, making it empty. The queue front and the queue rear, where are they going to be? Okay. So the queue rear, you want it to add to that first element. So you want it to be 0, okay, on a new array. The problem is to avoid having a special case where you have to test for all of that, all we're going to do is that we're going to set initially the queue rear equal to the max queue size minus 1. Okay, the max queue size in our case is 10. 10 minus 1 is 9. 9 is the largest possible index. If you set it to the largest possible index, no, I don't have a picture here, but if you set it to the largest possible index of 9, okay, when it's empty, when you go through the normal add queue, it adds 1 to it, which using the modulo makes it a 0, and it adds it in the proper spot. Okay. So that's all we're going to do there. So let's take a look at the code now and see how it's implemented. Okay. So the last video I did more of a type and talk. I'm just going to go through it this time because I think it should be getting clear kind of the way things are working. Okay. So we're going to include our qadt.h because we're going to extend that. Okay. We're going to inherit from that public inheritance. Okay. There may be an assert in here that I may need to see assert, but we'll see. So this one we have, again, because we have an array that we're storing, an array is a memory variable, we have to do all those things. We have to have a copy constructor, we have to redo the assignment operator, and we have to have a destructor. Okay, so this is just what the assignment operator is going to look like in our function prototype. Okay, it's a constant function. It's the operator equal. Okay, it's not going to change anything. It's just going to assign its operator equal sign. That's the assignment operator. It's going to create a new array or a new queue when you do that. Okay. Then we have our Boolean is empty queue, constant function. The Boolean is full queue, constant function, or constant in that it doesn't return or it doesn't change the queue. Okay. We have initialize queue, which is a void function. We have then the front, which returns the element at the front. The back returns the element at the back. We have the add queue, which takes a queue element. That queue element doesn't change, so that's constant. Okay, that's a pointer to that or a reference to that. And then we have the delete queue, okay, which removes an item from the front. Okay, so we have our constructors. The queue type we're going to set. The queue size is something that we're going to allow to be input when you create the queue. Okay. But if they don't put something in, we're going to set a default as 100. Okay. And then here's the copy constructor that takes another queue to make a copy of. And then finally, there's the destructor. Okay. So the variables we're going to have here, we're going to have an integer for the max queue size. That's the maximum number of elements you can have in your queue. We're going to have a count that keeps track of how many elements there are. We're going to use that to see if it's empty or not. Then we have an integer for the position of the front of the queue and a position of the rear of the queue. And then finally, we're going to have a pointer to an array that holds the actual data of the queue. Okay. So the is empty queue, straightforward enough. We're just going to see if count's equal to 0. Count's equal to 0, then it's empty. If not, it's not. Okay. And then for the is full queue, we're going to see if count is equal to the max queue size. And that will determine that. Okay. Here's where we initialize the queue, where we're going to set the queue front equal to 0, and the queue rear is equal to the max queue size minus 1. And then the count's equal to 0. So that's our initial conditions. Okay. The front, we do have an assert here, so I'm going to have to go back and add the C assert. I'm going to assert that the list is not empty for both front and for back. Okay, I'm then going to just return those positions. Okay, I'm going to go ahead before I forget. It's a good idea when you see something like this. I'm going to go ahead and come up and include the C assert. Okay. But I do have to spell include correctly. Notice the Emacs does show me that there was a problem by not highlighting it correctly. Again, if you're new to Emacs, if you haven't had me before, if Emacs doesn't format automatically, nearly 100% of the time, it's going to mean that you've got a typo or some kind of a syntax issue. Okay, so we've tested those, we've returned those. Okay, there's the back. So here's the add queue where we're going to use the modulo arithmetic. Okay. So we're going to, again, we're adding a new element to the queue. That new element's not going to change. If it's not a full queue, okay, so if the queue is full, then we just have to do the error message can't add to a full queue. Okay. So we're assuming or we're not assuming, if we're here, it's not queue. So we're going to let queue rear be equal to the queue rear plus 1 mod max queue size. Okay. So if it's at that queue or max queue size minus 1, it's going to automatically take it back to 0. Okay. We're going to increase the count by 1, and we're going to let the list at that queue rear position be equal to the new element. Okay. Delete queues, or we're going to get rid of something off the queue. With that, we're going to decrease, we'll undo what we just did. We're going to decrease the count by 1. Okay. And then we're going to let the queue front this time be equal to queue front plus 1. Again, we're going to mod the max size. So as things move around, if it goes off the right edge, it'll come back to the left. That's all we're doing there. Okay. Here we have the constructor, which is going to take a queue size. And if they enter a queue size that's less than or equal to 0, then we're not going to let them do that, give them an error message and set it equal to 100. If not, we're just going to set it equal to the queue size. Okay. The constructor is also going to set, just like the initialize did, the queue front equal to 0 and the queue rear equal to the max queue size minus 1. Okay. Then on the destructor, the big thing we're looking for here is to delete that list. The list takes up memory, so this will delete that. Okay. And that's the basic idea here. Okay. So that's in the book. You should go through the code in the book as always, and get a working copy of this. The homework will require that you have all of these data types typed in and ready to go. Okay. And like on the last problem set, we'll probably will be making modifications to it. So one more video to go. We'll talk about implementing queues as a linked list. And luckily that goes back to being relatively straightforward. The linked lists have more flexibility as far as memory usage than the arrays do. So this will look more like the array implementation of a linked list.